Hi, Rachel. Thanks for joining me on this episode of Concentrating on Chromatography. I appreciate it.
Thank you for having me.
Absolutely. So, I'm very excited to talk about your work today, and I'm interested to hear what originally pulled you into kidney cancer research specifically.
Well, it was something that I had a little bit of experience in during my undergrad, where I got to really start to work with kidney cancer. And so, given the short length of my undergraduate project, when I transitioned to my master's, I transitioned to something completely different, something more instrumentation focused, focusing on breast cancer. And so, when it came time to pick my PhD project, I was really excited about the opportunity to explore a new realm. And it felt like kidney cancer was this that I still could contribute in. And it almost felt like unfinished business and a way of coming back to the project that made me fall in love with research and asking those big questions that we didn't quite know the answer to yet.
And for those who are unfamiliar with you, where are you doing this work and who's your advisor?
I'm a PhD student at Queen's University in Kingston, Ontario, and I work for Dr. Richard Oleschuk in the Department of Chemistry and Dr. Chris Nicoll in the Department of Pathology and Molecular Medicine.
Great. Now, I'm totally unfamiliar with RCC, so I would love to hear about why are these cases specifically such a hard biomarker problem, and why do you think that there hasn't been more progress, I suppose, with the prognostic markers?
Yeah, so with kidney cancer, there's generally over 400,000 people diagnosed every year, and 75% of those cases are clear cell renal cell carcinoma, which is where my project comes in. And it's not that people aren't looking. There's been fantastic work in genomics and proteomics and metabolomics, and there are some potential biomarkers that have been identified, but there's very few overlap between the people that are finding some 8 biomarkers in one particular study versus a panel of 15 that seems to work well. So it's not that we aren't trying. I promise you we're trying. But it's cancer is incredibly, and kidney cancer is not exempt from that fact. So sometimes from patient to patient, there's variability. And so investigating and choosing the candidate biomarkers, which are selected for further investigation, is an incredibly challenging pursuit. And so I swear we are trying, but I do think that just the nature of the sample itself is certainly very challenging in finding prognostic biomarkers.
I read it was so challenging, and that's why we have to have so many people working on it, because it is such a pressing challenge that needs to be improved upon, let's say.
Absolutely.
My understanding was that RCC is often described as diagnosed almost by accident, incidental findings of imaging done for something else. How does that diagnostic pattern shape what a biomarker actually needs to do clinically?
Yeah, absolutely. In an ideal world, we'd have a diagnostic biomarker that would catch kidney cancer early, but at this point we don't. And so it's when we find kidney cancer by accident, we often find it at these later stages that have pretty poor outcomes. And so what a biomarker needs to do clinically is ideally find the kidney cancer early, but in the case of these incidental findings is give us as much information as we can get about how aggressive the tumor might be, and that will give us insights on how we can treat that patient.
And just in general terms, what does metastatic potential mean operationally in your work?
At this point, we're not trying to say that this patient has metastases. The current point of our investigation is to understand the biology of what happens to that tumor when it goes from a low aggressive tumor to a high aggressive tumor. And so we're trying to see what pathways change, what mechanisms change, and help us understand what is What is the tumor doing that makes it so aggressive? And once we understand that background, then we can go into figuring out what our markers might be to help us identify these aggressive tumors when they're identified in patients.
And it likely doesn't surprise you that we spend a lot of time talking about LCMS and GCMS on this podcast. It's focused on separation science and certainly chromatography in general. LCMS is still seen as the clinical gold standard, and certainly a lot of the audience has LCMS as their reference point. Why is AIMS the right tool for this specific question rather than a faster but lesser alternative?
Absolutely. I'll never make the claim that AIMS is here to replace LCMS. From my perspective, I see them as two very complementary parts of mass spec. AIMS is fantastic because it provides this rapid assessment and rapid screening method for clinical samples that provides a whole lot of molecular information as fast as we can, almost instantaneously. So in my case, I'm still in the discovery phase. So I want to know as much information about my sample as possible rather than trying to break it down into individual molecules. And so once I figure out which of the analytes are important using AIMS, then we can go into LCMS and separate those out and achieve a better quantification.
And the term minimal sample preparation means different things to different people. But what does your sample prep process actually look like currently?
Yeah, so it really depends on what sample you're working with. In my case, I am primarily focused on the use of cultured human cell lines. And so I have a rare opportunity to grow the cell lines myself. So a lot of my preparation involves growing those cell lines and then either lysing them via chemical lysis or a formalin fixation and paraffin embedding, and then sectioning for either LMJ-SSP or DESI analysis. However, if I was working with excised tumor samples, and of course I was in a perioperative setting or in a biosafety 2 lab, I could directly analyze the tumor margins with the LMJ-SSP. But really, it depends on what your sample is to figure out what those less sample preparations that are required.
And I'd love to run with that in terms of your pairing LMJ, SSP, and DESI rather than picking one or the other. What does each technique see that the other misses?
Absolutely. The LMJ-SSP is a fantastic tool, one that Richard's lab is quite specialized in. The LMJ-SSP is able to do a really localized analysis. It has the speed, and it's able to identify and analyze samples that have a varied surface topography, like an excised tumor sample. DESI has a fantastic spatial resolution, down to about 50 microns, whereas the LMJ-SSP currently sits around 1 millimeter, but it really depends on your probe's compositions. And so DESI can pick up on these elements of spatial biology that can be incredibly important as we move from a cell line-based analysis to tumor samples. And so seeing the spatial biology can give us insights into what the tumor is doing and the pathways that are really making the difference.
One thing that stuck out for the coupling of the LMJ SSP is you're using basically two different mass analyzers. What's the practical reason for why that's done?
So in my work, I'm using a triple quad mass spectrometer and a Q-TOF as well. The majority of my work is currently done on the triple quad. Its sensitivity and focus on the lower mass range, so the small molecules where my work is focused, allows me to go through the discovery process and identify the metabolites or the analytes which are statistically significant. From there, then I can perform SMS using the Q-TOF, so changing mass spectrometers to find those putative IDs and then trace it back to the pathway. So the two mass analyzers help me answer two parts of the same question.
In the automated XY sampling grid, just how large of a leap forward was that for reproducibility, and what did the sampling look like before that automation step was installed?
Many of the LMJ-SSP analyses, they were either done manually or through lab-built custom XYZ stages. What our lab is particularly proud of is that we've outfitted a 3D printer to facilitate this automated analysis. So one of our previous grad students made a custom-built software to control the 3D printer. So the 3D printer moves the probe around and allows really precise control over movements down to 50 microns, precise control over how long the probe is in contact with our sample, how long between sample touches, and it really makes a difference in reproducibility, because you can even control whether you're analyzing at the same Z height or at varied Z heights over the sample as well.
And you're working in both polarities across both the cell lines and both instruments. So that's certainly a lot of dimensions that you're working in. How do you keep the data analysis traceable?
I break it down to one mass analyzer at a time, and then one polarity, and then look at my two cell lines within that polarity so that I'm looking under one condition but comparing the two cell lines under that condition. So once I've selected my mass analyzer, so let's say it's triple quad, then I'm going to look at that time in the negative mode. Then I can compare between my low aggressive and high aggressive tumor models. I can move into my natural pre-processing steps, whether that be binning, normalization, transformation, dimensionality reduction, to help facilitate the finding of those discriminating features between the two groups. And then I can move on to a MSMS analysis. So that pipeline will be repeated for both polarities on one analyzer and then moved and done the same thing on the other analyzer.
One thing that's always exciting to me about the podcast discussions is that more often than not, there's a cool application of either AI or machine learning. And in your case, you were able to apply unsupervised machine learning. So I'd love to hear more about how that helped you in the process.
Absolutely. AIMS data, we call it high dimensional. They're massive data sets with hundreds of thousands of metabolites for many, many samples. And so machine learning really plays a massive role in being able to help us work through our data. For me, my initial analyses have included a principal component analysis, so an unsupervised dimensionality reduction technique. And we've been able to see that the two different cell lines, the non-metastatic and our metastatic, they separate pretty nicely, which is very encouraging. This is telling us that they do have distinct molecular profiles, even though they're both clear cell renal cell carcinoma, both kidney samples, but different molecular profiles. And so while this doesn't give us for sure all of the biomarkers, it is very encouraging that we're seeing initial separation.
So my understanding was that this was the first time that LMJ-SSP has been used to assess metastatic status. Was that scary to you at all, and what actually pushed you in that direction to apply something new?
Absolutely. I think with every research project, there's always the excitement of delving into the unknown. In my master's, I did a little bit of work differentiating between healthy and cancerous tissues, which are two very different biological states. But when you move into the same type of cancer, but different, whether it be non-metastatic and metastatic, the differences might be a little bit more nuanced. And so what pushed me into that was that I wanted to explore something that hadn't been done before, but something that was in great need. Specifically with kidney cancer, when it's found at these later stages, you have a much higher risk of metastases. And so this was an area that not only I knew that I could contribute in meaningfully, but it was an area that needed to be pursued.
In your long-term goal is a rapid, minimally invasive, MS-based prognostic tool. What would that mean for changing the actual clinical workflow moving forward if you were able to be successful with accomplishing your target?
Absolutely. Well, if I was able to find a diagnostic biomarker, then that could be incorporated into a standardized screening. Liquid biopsies are increasing in popularity, so looking at things like blood and urine. In my case, I would be interested in knowing if we could find a diagnostic biomarker in urine to catch cancer early. But if we were looking at specifically prognostic biomarkers, once that tumor is found, whether through pre-screening or through incidental finding, it's important to be able to tell what that tumor might do and to give it as much information to the clinicians as possible to help influence whether that patient received treatment right away or whether that was surgery, to hopefully improve patient outcomes. So the way that I see this is never to replace these standard clinical workflows, but to help complement them and support them.
For clinical researchers or anyone who's especially interested in this topic and where this work is headed, what should people be paying attention to right now to kind of stay up to date with the latest and greatest advancements? And I don't know if that could be in the form of conferences that you find to be most helpful or assets online, or what does that look like to stay up to date on this work?
I think I have benefited greatly from interdisciplinary work. My work is inherently involving chemists and pathologists and computer scientists, and through discussions with these people, everybody has their own area of expertise. And at least from my perspective, it's impossible for me to stay up to date on everything. But if you are reading the literature and speaking to other people in the field, you become knowledgeable in, let's say, analytical chemistry. But by collaborating and working with people in other fields, that gives you a great resource to stay up to date in what's the most important across many different fields.
And what would you say is the most surprising thing this project has taught you about kidney cancer biology that you may have not expected to learn heading into the project?
I mean, I'm a chemist at the end of the day, and this was not a project that I saw myself taking on, but the way that working with these clinical samples, it's changed the way that I approach research. As analytical chemists, sometimes we get so hung up on building these new tools or developing new methods, but we forget the impact of our work. We forget about how important it is to not only think about what we do in the lab, but who it impacts. And so delving into kidney biology and thinking about those patients that my work could impact really makes every step of the process incredibly thoughtful and meaningful.
Do you have any advice or just general thoughts for grad students considering analytical chemistry applied to oncology?
This is an incredibly exciting time to be working at this intersection of chemistry and oncology. There's the potential that combining these two highly complementary fields can provide answers to questions that would otherwise take a very long time to answer, and give insights that may not have been found. And I know that working at this intersection, my day-to-day can include anything from troubleshooting instrumentation issues to pathology to working on new statistical analyses. Every day I'm learning, and it gives a new opportunity to collaborate and contribute. And so if you are considering work at this intersection, I can't recommend it anymore.
That's great to hear. Rachel, is there anything else from this project or your lab in general that we may have missed that you want to share with the audience?
I think any opportunity to collaborate brings about new perspectives and new opportunities. And my lab is a combination of chemistry and pathology. We work with computer scientists and surgeons and med students, and any opportunity to bring new perspectives to light is incredibly exciting.
Rachel, I really appreciate you sharing your work with the audience. This has been super insightful, and it's really cool to focus on such a important clinical lab project. And I think we did a decent job framing it in terms of how your work is somewhat adjacent to LCMS, which I think is the reference point for most of the audience. So thanks so much for your time, and I greatly look forward to hearing from you in the future about where this work is headed.
Thanks for having me, David.